Okay, so good evening everybody and welcome to the engineering group of the Geological Society's July evening meeting. Tonight we welcome David Place of Mott MacDonald to be presenting on the Accelerated programme for Crossrail's Moorgate shaft. So without further ado, I'll pass on to David to give his presentation.
There we go. I was hoping we were going to get this slide. Go back, please. How did that happen? That's it, right. I was intrigued, actually. I looked at this slide when Tom sent it to me, and I looked at this date, 1807. I thought the Geological Society, I'm sure that's before the Institution of Civil Engineers was founded. So it's a great privilege for me to be here this evening. My theme, as we're in the engineering group, is actually going to be the interaction between ground and structure. And as Tom said in his introduction, if I can persuade this, there we go. Right, effectively, what I'm going to talk about is a case study from work that was completed in 2015. So this was on Crossrail, and I'm sure you're all well aware that Crossrail is frequently described as the largest civil engineering project in Europe. What you can see on the screen here is in the red is the central section, and that's all in tunnel. And I move on to a long section, and what you can see there highlighted is the position of Liverpool Street station, right under the City of London, and the Crossrail tunnel there is at its deepest point on the whole of the central section alignment. Tunnels are constructed by TBM, and in the top left corner there you can see a picture of one of the TBMs. The orange highlighted section there is the Y drive, which was the programmed critical tunnel drive on the whole of the Crossrail project. So starting from a launch site in the Limo in March 2013, it was due to go through the Liverpool Street site in November 2014 and onwards to Farringdon, where it was due to arrive in 2015. And this was programme critical because the follow-on activity after tunnelling is track installation. And again, they were starting from the Limo site or further east and working towards the west. So let's get a pigeon's eye view of the site at Liverpool Street. I say Liverpool Street, actually what you can see running top to bottom is Moorgate, and the Moorgate shaft, named after its location clearly, is at the west end of Liverpool Street station. Stations on Crossrail are fairly unique. Typically, one end of the station would be, say, at Moorgate, where it has its own London Underground and Network Rail station, and the other end would be at Liverpool Street, which has a different London Underground station and a different Network Rail station, so that the tunnels for the stations are very long. And the usual arrangement is to have dual entrances, one at each end, so the catchment area is very large. So the actual site of the shaft is highlighted there. You can see, obviously, City of London, so that was a site that was built upon. And if we have a look, the site that was taken was previously occupied by the AMRO Bank building. This was a 1970s concrete frame building, 6 stories in height, had a single-story basement. It spans the London Underground Metropolitan Line subsurface tracks, and it was founded on quite a large number of 900 mm diameter board piles, lengths of approximately 34 meters. So quite substantial foundations. The building was taken possession of in advance of the main Crossrail works, and was demolished down to floor of basement level. The basement floor slab and obviously the supporting piles were left in the ground by the demolition contractor. So let's just have a quick look at the site. You can see the Moorgate shaft there is that turquoise polygonal figure. Not the ideal shape for a shaft, you'll agree. Ideally, we'd like them to be circular. So an idea of the size of this thing, it's 35 meters in east to west and similarly north to south. It's down to 42 meters below street level, so we believe it's the deepest basement ever constructed in London. And the main shaft is formed by a 1.2 meter diaphragm wall towed down to 55 meters. As I said, ideally you would want a circular shaft, but within the constraints of the available site, if we put a circular shaft in there, we just did not get a large enough cross-section area to get all the equipment and whatnot that we needed in there for this to be a functioning means of entry and exit from the station. If we, because it wasn't circular, we had to help out the polygonal shape to resist the soil loads as the excavation took place. So there's a double strategy for that. We had two temporary strutting walls constructed at the same time as the main perimeter diaphragm wall, and we had 7 ring beams, which effectively are creating that circular shape that is the most structurally efficient for supporting the walls of a shaft against the earth pressures from without. Now, if we peel off the surface level, let's just have a look to see what we've got immediately below the surface. Well, so to the north of the shaft, we've got the subsurface tracks of the Metropolitan line, which are in the region of 130, 140 years old now. To the east of the shaft, we can see we've got the tunnels of the Northern Line. These are deep level bored tunnels, cast iron linings. They're only 100 odd years old. And then if we peel down some more, what we can see is going under everybody else's tunnels right at depth, and this is why this is the deepest station in London. We have the tunnels for Crossrail itself. The one running, let's see if I can get the pointer to work. No, can't get that to work. There, the one running across the top there is the eastbound tunnel, and the one that comes in from the right and goes into the shaft is the westbound tunnel. And this is fairly unique here because of constrictions on space for where the tunnels themselves could be bored. The westbound tunnel actually had to pass through the bottom of the shaft. So there is an interrelation between the construction of the shaft and the construction of those tunnels. And as I said earlier, the tunnels themselves are on the critical path for the delivery of the whole of the Crossrail project. So, once the shaft has been sunk down to its bottom level, a launch chamber for the TBM can be constructed. The TBM can then be transited through the shaft and then launched from the far side of the shaft, and will then continue the drive towards Farringdon, where it finishes up. So the TBM going from east to west on the westbound tunnel was called Victoria. The one going the other way was called Elizabeth. Right, let's just have a quick look at it in 3D. The shaft itself is the green structure. The new surface level ticket halls above the shaft are the sort of pale blue structure. You can see the brown is the Metropolitan line. Oh, I've got the date there for you, 1875. So yes, just over 100 years old there. You've got the Northern line running above the Crossrail tunnels, and you've also got the old post office railway there as well. And then you've got various linking tunnels, escalator barrels, vent relief shafts for the Crossrail station. So let's just have a look in cross-section now. The Northern Line tunnels, as you can see, are very, very close to the shaft. We're looking at them being not much more than a tunnel diameter from the diaphragm wall. Crossrail had an asset protection consultant whose role was to come up with the criteria to protect all assets adjacent to the works as Crossrail was constructed. So these will be building assets on the surface, underground assets such as the Northern Line tunnels. So what could happen to the Northern Line tunnels? Well, as we see the shaft, and the shaft is excavated in stages, the ring beams are built, or I'm not illustrating those here. As we go down, irrespective of the temporary supports or permanent supports we might put inside, those diaphragm walls will be pushed inwards by the soil pressures. And as those diaphragm walls move, then the lateral ground movement will cause the ovalization of the Northern Line tunnels. Now, the Northern Line tunnels were the very first deep level tunnels on London Underground, so they are the smallest diameter, and even though they were enlarged, so they're no longer a true circular shape, the running clearances to the rolling stock are very, very tight indeed. So any loss of shape through ovalization would be quite critical for safe running of trains. The other thing that's going on that will affect the Northern Line tunnels is the sprayed concrete lining tunnels. So these effectively are the large tunnels for the station platforms, and they're not constructed by TBM. TBM is dragged through them. These are constructed by progressive excavation of the face with sprayed linings. So as they are excavated forward, what will happen is the face loss through the tunnel causes soil flow downwards, and that will cause settlement of the Northern Line tunnels. Now, these two things aren't happening separately, they're happening at the same time, or in a sequence. So the asset protection consultant, when working out how much wall movement could be permitted on the Moorgate shaft, and working out how much movement could be permitted while the SCL tunnels were excavated, had a delicate balancing act, and so some settlement tolerances were allocated to the tunnel construction and some settlement tolerances were allocated to the shaft construction. All this was in advance of anything starting, so as you can imagine, to be safe, to protect other people's assets, Crossrail had to adopt worst credible scenario. Right, so let's just have a little look, see in more detail what's happening at the shaft. You can see that the main Moorgate road is up there with the Northern Line tunnels down below, and a sewer shallower depth under the road, and you've got the upper escalator barrel coming up and passing over the top of the Northern Line tunnels. You've got another access into the bottom of the shaft, which connects through to the station platforms going in below the Northern Line tunnels. So within that shaft, we have to provide vertical circulation for the passengers getting on and off the Crossrail trains. We have to provide tunnel ventilation, and then, as there always is, there is a huge volume of plant rooms as well. So the upshot of the assessment by the asset protection consultant was that in order to safeguard the Northern Line tunnels from the effect of the shaft sinking, there was a red trigger level on wall movement of 30 millimeters. That is not a lot. Ooh, shouldn't have done that. And the other thing that was going on here as part of the tunnel construction for that upper adit at the top of the escalator barrel, which has come out of the London clay and is into the sort of made ground and whatever, which is not good for tunnel excavation, was a very large program of permeation grouting to firm up the ground. Right, so looking at a quick cutaway of the shaft, what we've got is vertical circulation, so you've got escalators, stairs, and you've got lifts for passengers. And then you've also got a lot of plant rooms for and equipment access shaft to get the plant into those plant rooms and change it out during the lifetime of the railway. We've got the escape stairs, which have got a capacity for 800 passengers a minute, because you've got to evacuate your station platform in 4 minutes, and you've got a train that's got 1,200 passengers on it, and they might all have to come up these stairs. So the stairs are quite large, as you can imagine, and we've also got tunnel ventilation. Now, tunnel ventilation is made up of a number of components. You've got the forced ventilation, because if you've got fire in the tunnel, you need to be able to push the smoke away from the means of escape for the passengers. You've got draft relief so that the piston effect of the air pushed in front of the train can be mitigated. And we've also got smoke extract from the station platforms themselves. And at the end of next year, when you go down there, you'll see that the crossrail platforms in the tunnel section have all got full height platform screen doors, primarily for smoke control. Right, archaeology. I don't really want to talk about archaeology at all, but it gives you an idea of what those upper levels are. You can see that we've got something like 5 meters of made ground above the old Roman level when the Romans first occupied London. Now, obviously, because this area had been occupied since Roman times, Crossrail were very keen to maximize the availability of the site for archaeological investigation. And here you can see this is the main road outside. On one side is Liverpool Street Station, the other side is actually my office. And you've got probably the biggest archaeological dig in London going on here. Some of you might have seen a very interesting television program where this was shown. And if we move on, right. So the superficial geology, this is what we thought was probably there. Some sort of scour hollow and old riverbeds. That hollow is obviously drift filled over time, and what you can see there is an attempt to contour where we thought the surface of the scour hollow is, basically sourcing information from boreholes, pilorizings, and instrumentation. So if we look at a vertical section through the geology, and we have to get the word geology in because I'm aware of which building I'm presenting in. So we've got something like 5 meters of made ground, then the terrace deposits, and that's where that permeation grouting is going in that I was talking about earlier. Then we've got a reasonable amount of London clay, 20 to 30 meters. Below that is the Lambeth group, and under the Lambeth we've got the Thanet sand, and then the chalk down below. We don't really have, in terms of the engineering of this project, the chalk is so far away, we don't really have to worry about that. But certainly the rest of it we do need to worry about. So obviously one of the questions we had was where is that surface profile of the drift-filled hollow? So if we look at the groundwater conditions, here you can see we have a lot of variation. So we've got hydrostatic variation with groundwater pressure with depth for the upper part. Then pressure slightly decreasing, and then we get out of the bottom of the London clay, and all of a sudden we've got a big reduction in groundwater pressure in the Lambeth group, and then it builds up again down to the lower aquifer. So what we've got here is a very underdrained condition, and that when you're sinking your shaft down, you're very concerned that as you go down with your excavation, all of a sudden you don't get geysers of water spurting up through the floor of the shaft. Right, let's have a look at the shaft in slightly more detail. As I said, it's a very irregular polygonal shape. The diaphragm walls were standardized into a number of standard panels, and then some very strange ones at the various corners. And then, as I mentioned earlier, we've got these strutting walls, And Strutting Walls had two components. We had basically an unreinforced concrete panel, which is the grey, and then we had panels, again unreinforced, but with plunge columns dropped into them. And those plunge columns were dual purpose. They extended right from the below the base of the shaft level right up to the surface, and they were initially to serve as the legs of a jetty for the crane that was operating the grab to remove material from the shaft and drop equipment and such like into the shaft. And they were also lower down incorporated into the permanent works of the shaft. And the idea of these strutting walls, as you can imagine, is to prevent the inward movement of the long wall to the east of the shaft and by propping it back to the shorter wall on the west of the shaft. Remembering that the Northern Line tunnels are only a tunnel diameter about 6 meters away from that long east wall. Right, so let's just have a look at the construction sequence for the shaft. So as I said earlier, the building that had previously occupied the site had been demolished down to basement level, and that was on pile foundations. As you can see on this cross section, you've got London Underground, the Metropolitan lines to the right of that basement, and on the other side of the basement, to the left of it, you've got a listed building. So the construction sequence was to sink the diaphragm walls, then sink the strutting walls, then put the plunge columns in, having got to there, capping beam on top, and with the capping beam on top, then we're ready for start of excavation. So excavation was in stages, and at each stage a ring beam was built. You can see the sequence here. And then having got the ring beams in, we can't take the ring beams all the way down to the bottom of the shaft, because I said earlier, the train itself runs through the bottom of the shaft. So we get to the bottom of ring beam 7, and that's it for the ring beams. So we need to, if we have to, we need to find another way of supporting the walls of the shaft during continuing excavation. So there were two ways of doing this. Those green objects, which are called slab strips, are part of the permanent works. And again, they are running in the east-west direction, and they perform the same function of the strutting walls, which are broken down as we excavate the shaft. And then below them, we have 2 levels of propping. And this propping was envisaged to be a steel tubular sort of arrangement in a spider's web, which I'll show you in plan in a moment. And then beneath that, then a very thick concrete base slab. And then once the base slab is in, the temporary struts come out, lining walls go in with tunnel eyes, and then the tunneling machine will come through. So the temporary propping looks like this. You can see it's a spider's web. That's got to be lowered down through all the ring beams to get the first level of propping in. Not easy. It'll have to go in piecemeal and be assembled down in the shaft. And then the second layer actually has to be threaded through the layer you've just built, which, as you can imagine, is even less easy and potentially could take quite a long time. And that propping then required wailing around the D-wall inner faces. And that temporary works design for that was left to the contractor, as it was seen that he would have the opportunity to utilize the lining wall as the wailing as well. And as I said, the lower level of propping has to go in after you put the upper level in. So here's the contractor's modeling of what it would all look like. So you can see that shaft is quite busy in there. You've got the jetty on the steel plunge columns where his crane is sitting, and then you've got the ring beams, and then below that you've got the 2 layers of props, and then the red is the permanent base slab. So here is the construction program. The way the contracts for Liverpool Street Station were awarded, I've already talked about an advanced works demolition contract for the Moorgate shaft site. There was then a contract specifically for the construction of the Moorgate shaft down to completion of the shaft. The rest of the station, bar the tunnel elements, was a further contract. And so the contractor who built the shaft would then hand over to the main station contractor, who would then fit out the shaft. Effectively, the shaft goes down with the top-down sequence to base slab level. It's then handed over to the tunnelling contractor who does the spray concrete lining tunnels. It's then handed over to the TBM tunnel contractor who drags the TBM through and launches it out the other side. It's then handed over to the station completion contractor. So some very large number of contractual interfaces, all of which have got key handover dates. So you can see program criticality here is a big thing. So that was the original program. Now just cast your mind back to that old bank building with the piles, 34 meters long. Now it was thought from drawings that were available to the designer that the piles that supported that building did not conflict with the position of that very strange polygonal shaped diaphragm wall. Sadly, when the contractor arrived on site to build the shaft and removed the basement's floor slab, he found that the piles weren't where they were expected, and some of them were indeed right on the line of the diaphragm wall. So there was an 11-month delay to the start of the diaphragm walling, while the contractor, or in fact effectively the diaphragm wall subcontractor, Bauer, had to go away, invent a device for extracting 34-meter long board piles, test it, bring it to site, and extract the piles. So that's and I'll show you how this happened in a couple of slides' time. So piles were duly removed. Diaphragm walling then went ahead, and actually the actual diaphragm walling time speeded up on the original program. But you can see when you look at the sequence of building the ring beams and then all the other temporary props to the base slab, we were way beyond the key date for handover. We effectively had a program bust here. We saw that as the designer, and we talked very closely with our Crossrail client, and we proposed a concession against Crossrail's civil engineering design standards, which were used for the design of the whole project, which we proposed to do a 3D analysis of the whole of the shaft construction sequence with undrained soil conditions. And undrained soil conditions could be used, but the proviso was that work had to be completed within 12 months. And at the moment, as you can see from the program, the work was not going to be completed in 12 months. So there was a bit of a challenge here. We needed to come up with ways of making it quicker to build, so that we got within those 12 months, and then we get the benefit of using the undrained conditions. Right, so set that aside for a moment, and just to close out on the pile extraction, what you can see there is one of the old piles with its rebar cage sitting in the ground. Now, Bauer came up with a very cunning device. So first thing they did is they drilled into the top of the old pile and grouted in a threaded bar. They then built a guide wall around the pile, and then with their clever machine, they bored a relief hole. So they exposed the full length of the pile with a machine which was called an annulus cutter, which looked like this. And then they just lifted the pile very slightly with that grouted in threaded bar so that they get an idea of its weight. And then that's done by jacks. And then once they know how much it weighs, then a very large crane lifted the pile out. And then it could be cut up in sections on the site and trucked out of central London for disposal. So there's the annulus cutter mounted on the Bauer rig. And you can see there, looking down the annulus, that it's cut. So what you can see on the right is the fat grey object is the pile, and coming out of the top of the pile is the rod that's grouted in so that it can be lifted out. And there it is, ready for lifting out. And here you can see it's been lifted out. So that's how the pile obstructions were overcome. So program acceleration, back to the main theme of the evening. As I mentioned, a concession to allow undrained conditions on the active side was obtained. And then further analysis, redesign, showed us that we could omit the temporary propping at the lower level. So that's now got crossed out with that nice red cross, and that's the one we really wanted to get rid of first, because that is the one that is most difficult to get in, because you had to thread it through the upper propping. But we weren't satisfied with just stopping at that, so we then looked at constructing the ring beams in bigger bites, so a deeper excavation and again, so saving construction time. And we also identified that potential emissions and other potential emissions of temporary works and changes to the construction sequence. Ideally, we wanted to omit the other level of temporary steel propping. We wanted to omit those green slab strips because they were oversized for their temporary works condition. In the permanent works, they were just a floor slab with a small downstand beam. And we also wanted to see if the last pair of ring beams could be excavated and then concreted in one stage. So what we proposed to Crossrail, and they accepted our proposal, was that we would adopt what we called a verification process, so that we would use intermediate blinding strips to control wall movements and mitigate ground softening during the excavation. And so we'd already started the excavation, so this upper work had been done, but then onwards, at the bottom of each stage of the dig, we would put a temporary blinding slab in, build the ring beam, then break out the blinding slab, do the next excavation, build the ring beams, and keep going down in this sequence until we got to the underside of the ring beams. And then after that, we would go down another blinding slab if we found that we had to put that level of propping in. If we didn't have it, then obviously we wouldn't have the blinding slab, and we'd dig down to the underside of the permanent works base slab as quickly as possible. So we did our analysis using a FLAC 3D model. What you can see is the structural model. So you've got the shaft and all the associated tunnels. What you can't, and that's 55,000 shell elements in the model. What you can't see is the 270,000 brick elements that represent the ground. And this model was a progressive model mirroring the actual construction stages. A lot of the tunnels had already taken place before we started this modeling exercise. The upper part of the shaft had already been constructed before we started this exercise. And then we got the tunneling program, and so we looked at the most likely continuing construction sequence to completion of both shaft and tunneling works. For the ground, we adopted what are known as A-star parameters based on a paper back in 2011 by Edington and O'Brien. And it was our intention to back analyze monitoring results from the shaft to see if we could refine those A-star parameters to represent behavior that we were seeing with the shaft ground interaction. So the ground parameters, as you can see, we had quite a lot of geotechnical data at various levels through the ground. So these two graphs show the parameters for the London clay. Originally, we'd started with a tangent shear stiffness against strain profile based on Jardine. which is the yellow line. For the start of the finite element analysis using the model I just showed you, we use what's called on this graph the blue line, the initial A star, and then where we got to is the red line, where from back analysis of actual wall movement, we modified those A star parameters. And we did that both for the London clay and the Lambeth group. So the verification process itself, we saw it as an innovative way of using real-time site data to re-engineer the design. So if you like, you could think of it as a reverse of the observational method. If you think when you're digging a tunnel using the observational method, you're working away and you have in your back pocket a whole series of mitigation measures that you will only introduce if you get certain movements beyond various thresholds. We're the other way around. What we have is a complete design. All those mitigation measures are part and parcel of the original design. And what we're doing is using the observed data to demonstrate that those elements can actually be omitted during construction, thereby speeding up the whole of the construction process. So the initial position, we always had a fully assured design. And in fact, we needed a fully assured design all the time. So what we had to do is, as we recalculated leaving various propping elements or whatever out, we had to get that verified and signed off by our category 3 checker as we went along. So the contractor started off with all of those works, the propping and the mitigation measures, including the slab strips, on his drawings, and he would be told as his work progressed by the employer if he could omit one of those levels of props or whatever it was going to be. What we identified was 3 verification points, at which stage each of those we were going to identify what could be, if anything, could be omitted, and what we would continue to keep in the design. So I'm going to show you a verification process flowchart. Please don't try and read this. This is just to show you the complexity of the issue. The words are not effectively going to help your understanding. The key thing really is we've got the construction stage in the contractor's program, and we've got the dates in the contractor's program. So everything we did as the designer and everything that had to be verified by our category 3 checker had to be done so that the contractor's construction program was not delayed. So that set us a very tight time scale to do our reanalysis and feed back into our reanalysis real-time data from the work as excavation progressed. So these are the 3 verification stages. So on the left-hand one, we've basically got a blinding slab at stage 4 of the construction sequence, and we're using the A-star parameters. And at this stage, we wanted to, if we could, form a view as whether the slab strips, those green rectangles you saw earlier, could be omitted. The next stage, when we got down to the next level of dig at stage 6, was, and we intended to use modified A-star parameters that have been derived from back analysis up to stage 4, is whether we could combine stages 7 and 8, which was the 2 ring beams, and the excavation for them. And then at the final stage, at stage 8, we would be using the modified A-star parameters again, and this is the big win ticket. Can we omit the lower level of steel propping? Because with that steel propping in place, it would obviously constrain construction of the base slab, and that propping would have to be taken out in order to let the tunnelling contractor get in to do the launch chamber and for the TBM to be taken through. So that was the really big win. Right, so this is a plan of the shaft, and those blue circles are the in-place inclinometers. And this was our primary source of data on wall movement during excavation. I have to say the contractor who installed these had a very nice setup. So effectively what you see is what we had on the screen in our design office. And if you move your mouse in and clicked on that inclinometer there, you get a drop down, and there you are. You see, you've got the wall movement from that inclinometer, and each color line represents a different date. So you can see over time how the wall is moving. And I would thoroughly recommend to all of you, if you're ever working on a project where you're doing this sort of real-time back analysis for information, to have information data like this is really, really good, because it does really speed up understanding of what is going on. Right, so here we are. This is the state of the game at the first verification point. You can see there's the contractor's jetty. You've got some ring beams in there. You've got temporary blinding at the base of the dig. So let's have a look and see what we've got in terms of data. So that's what we measured in the north wall. That line there is what was predicted before we started the verification process. So what you can say is that the prediction overestimated the actually measured movement by quite a large amount. And when we got to, so what we did is then we looked forward by modeling the next stage of excavation to see what the movement would be by the time we got to verification point 2. And that to us looked reasonably conservative. However, when we looked at the east wall, this is what we saw. There's the movement actually measured, and you can see it's more than we got on the north wall, for example, which was a bit of a concern. And the other thing you can see is the predicted before the verification process and the predicted at verification point 2 are both less than the measured. So something is not as we thought here, which was unexpected. So one of the things we questioned was how effective were those east-west strutting walls. And so at this stage, we were able to conclude that we couldn't make a yes or no decision on the omission of the slab strips. So that was held over to the next verification stage. But we still thought that the combination of stages 7 and 8 was likely to be possible. So we moved on. So here we are. We can see the works now as we get to verification point 2. You see the excavation's got deeper. There's another ring beam in there. You've got a blinding slab at the base of the excavation. So if we look at the data for the east wall now, when we've gone deeper, here's the measured. And we've got the predicted, assuming the strutting walls have got reduced stiffness, and the brown line you can see is what we should have got if the strutting walls were performing as we had expected them to. And blue lines just appeared, I think. And so what we did is we tried to match the measured wall movement by adjusting the stiffness of the strutting walls. And you can see that blue line there is at in the ground level, which is obviously where the strutting walls still are. Above the ground level, they've been taken down with the excavation. You can see if the strutting walls are only providing 10% of the expected stiffness, we're getting quite a close match there. The other thing that was a concern for us was that the green line, the predicted line, was exceeding the red trigger level, which was not good. And so what we then did using our model is we projected wall movement to the final stage. And here again, you can see the wall movement is exceeding the red trigger level. What was still a concern for us was our failure to match measured wall movement in the upper levels. So we went back to consider why that might be the case. So what we concluded at this stage is stages 7 and 8, which is the dig and the ring beams, could be combined. But again, we deferred the emission of the slab strips to the next verification point. So as you can imagine now, we've deferred the slab strips to the last verification point. We've also got the removal of the steel temporary works propping at that point. So there's a lot hanging on the next stage. So here we are. There it is at the next stage. You can see the excavation's gone deeper. There's some more ring beams in there. We've still got a blinding slab at the bottom. So let's just have a look and see how we got on here. So with our best estimate of the ground parameters, and here we have now, in our model, added in for the effect of the permeation grouting in the upper layers. We have tweaked the geometry of the ring beams and their stiffness. We've also added in the propping effect from the temporary works jetty, and we've got strutting walls, which have got 10% of the original stiffness. And what we're finding is we've now got a good match between predicted and measured. If we go back to a more conservative approach, what we can see is we are still exceeding the trigger level. So what we did at this stage, if you remember, I was telling you that the asset protection engineer had put a 30mm red trigger level on the shaft construction. That was our share of the asset protection. And on the tunnel construction, they also had a share of asset protection. So some of the total movement that was expected was going to be attributed to the shaft and some of it to the tunnelling. Now, by this time, the tunnelling was complete. So we knew how much settlement had actually occurred due to the tunnelling, and we were able to utilise the fact that the tunnelling had caused less settlement than had been expected, and therefore the asset protection consultant was able to allow our trigger level to be relaxed from 30mm to 40mm, which meant that even with our conservative estimates of the structure and the ground parameters, we were still not going to breach that red trigger level, which was extremely good news for us, because that meant under both service and ultimate conditions, we had a safe design. So we concluded at this stage that the slab strips, those green rectangles, could be removed, and more importantly, the steel temporary works propping below the bottom ring beam could also be omitted. And that's how we progressed. And if you see that dotted blue line that's just appeared, that in fact is the measured wall movement as the excavation went right down to underside of base slab. And that was actually still within the original trigger level. So conservative was, in this case, conservative, and our best estimate actually was a very good estimate. Right. One of the things I drew your attention to earlier was the discrepancy between the observed movement of the east wall at the upper level and what we predicted. So what we had a look at was temperature effect. So if we look at temperature over the months of April through to July, You can see gradually increasing temperature as we get further into the summer, and you've got small spikes up and down, which are the daily variation, and then you've got sort of more seasonal on top. Now, if we compare that with, oh, sorry, the blue line was the wall movement. So that's how the wall movement moved. And as you can see, it's it's an increasing trend, and it varies up and down. Now, if we look at the temperature, what you can see, if we look at falling temperature, right, which is the red line, you can see that wall movement increases. And when we look at rising temperature, which is those, you can see that the wall movement decreases. So effectively, what's happening here, as the diaphragm wall gets colder, it contracts, moves away from the soil. As it gets warmer, it pushes back into the soil. But of course, when it gets colder and shrinks, moves away from the soil, it doesn't leave a gap, the soil follows it. So when it gets hot and tries to expand again, it's got to push the soil, and it can't push it back to where it was. So what we're getting is a sort of, whilst we've got rising trends in temperature, we've got a rising trend in wall movement, what we're getting is a ratcheting effect. And this was not just happening on the east wall, it's happening on all the walls. So that was useful, and I'll come back to what happened on the east wall in a minute. But before I move on to that, I just want to say a few words about the strutting walls and why that 10% of the original envisaged stiffness was giving us a good fit lower down in the shaft. So our original design for the junction between the strutting wall and the diaphragm wall was actually a T-shaped panel. So that panel is built as one. Now, the contractor actually proposed an alternative way to construct this. So he built a wall panel for the main perimeter wall as a flat panel, and then he built the strutting wall panel up against it. And apparently he persuaded the engineer that he could clean the joint between those two panels so well that it would be a concrete to concrete joint. Our suspicion was that joint wasn't clean and there was something in there, something called clay, which is not as strong as concrete in compression. So as we excavated down into the shaft, here you can see the joints, and if we go in close, sadly, concrete smeared with clay looks very like clay, but you can see down the middle there, you can see a darker grey strip, which is about 60 millimeters in width, and that is what has softened that strutting wall, that little strip of clay between the strutting wall panel and the main perimeter wall panel. Right, anyway, let's just see how we got on with recovering the program. That's as we left it several slides ago, where the construction of the wing beams was busting us well past that handover date. So with the verification process, the accelerated program got the ring beams completed, and we were able to emit both the slab strips and the 2 layers of temporary props. So we actually ended up completing the base slab ahead of the original program. So we got a 14-week program saving. As I said, the base slab was completed 2 weeks early, and the handover to the spray concrete lining tunnel contractor was right on the project critical milestone. And you can imagine Crossrail, of course, were very happy about that. And the base slab concrete, as photograph of that, was poured on the 1st of November 2016. The delivery manager, Crossrail's delivery manager for the central section, Bill Tucker, said this achievement is a combination of an extraordinary story of collaboration between the contractor, designers and Crossrail. And looking back 6 months ago, there were many doubts about the ability to excavate, construct and bottom out the shaft on programme, and the teams did it. And we certainly did. We entered this for the ground engineering awards, and we actually took, in 2015, we took the Editors Award, the top prize. Here you can see the start of the TBM launch tunnel at the bottom of the shaft, below the lowest ring beam. And there you can see TBM Victoria as she comes into the shaft to transit through and be launched for her journey towards Farringdon. So lessons learned. Lesson number 1, know your geology. If you're going to do some good quality engineering, you need to have specific ground parameters at your site. Beware overly conservative design rules, because these can lead to extremely extensive temporary works and a lengthy construction program, which is what we had at the start. I think we've demonstrated quite conclusively that an observational approach using real-time information can provide a quicker and more cost-effective way of achieving the same goals. Use of 3D modelling with site-specific ground parameters can replicate very closely observed field behaviour. But in order to get there, we do need high-quality real-time instrumentation. We certainly felt the blinding slabs were a very effective way of controlling wall movements, and we conversely felt that the strutting walls were far less effective than expected. I think if we designed this shaft again, we wouldn't bother with the strutting walls. We would just go for blinding slabs. And I think this is a very important one. If we're going to use an observational approach, then we need close collaboration between the designer, the contractor and the client. We started off with very good collaboration between designer and client, and the contractor, bless him, whilst a bit skeptical at first, actually, because he was fully briefed in all the time, he very quickly realised that he could get himself out of a very nasty fix in terms of overrunning programme and liquidated damages and all those horrendous things that contractors don't like. And once he saw that there was a good chance of this working, he really rolled his sleeves up, got on with the excavation works, got quicker and quicker, got on with the ring beam construction works, built those quicker and quicker. And obviously, you know, we were feeding him construction drawings that were progressively being updated and assured by the Category 3 from Checker, and that had to be done and was done in very short time frames. And finally, we felt that the combined effect of the grouting, which stiffened the ground prior to the tunnelling, definitely had an effect on the ratcheting of the east wall, which is why as the wall, the diaphragm wall expanded with increasing temperature and was pushed back into the soil on the east wall, where the soil had actually been strengthened and pushed towards the wall by the grouting, you had a much bigger task for the wall to push the soil back, and that's why at that wall we got those much larger movements. Right, few items of further reading. This is the paper I mentioned about the A-star parameters by Edington and O'Brien. There was a further paper by O'Brien and Harris which developed the same thing further. The paper by a colleague of mine, Adrian Douglas, on the construction of the base slab in the shaft itself, which was in ICE proceedings in November 2015. And there's a paper by my colleagues and myself, which is in the Crossrail Project Infrastructure Design and Construction Volume 3, which was published last year. You can't miss it. It looks like this. And you can't miss it twice over because a copy of that paper will be made available to members of the Geological Society by the event organisers after this meeting. Right. Please be aware that I am a civil engineer, not a geologist or a geotechnical engineer. Nonetheless, I will take and answer as many questions as I can.
Okay, so if we can start with any questions, guys. If you've got any, then raise your hand, and then I'll bring the mic to you. You can just outline your name for the people who are watching at home. That'd be great.
Kieran Quigley, MacDonald. I just wondered about your timeframes for delivering the reanalysis after the looking at the monitoring data, and how did it work? Were they realistic, or did you not sleep for 6 months?
We were confident that we could do it in the time frame. We were also confident that the guys who had to deliver it would actually not sleep for 6 months if they had to. You know, this is a team effort, and the guys who worked on it, particularly doing the flak analysis and processing the information from the monitoring, I have to say they worked really, really hard, long hours during the week and at the weekend.
Good pitch from Mott. The other one was the stiffness parameters that you gained from the monitoring. Were they updated every time you did a new dig?
No, we didn't continuously update soil parameters. You know, the soil is a multi-layered soil, and potentially some of those layers, for example, the London clay in particular, may well have variation with depth. So, what did I say? 270,000 brick elements representing the ground. So you have to be very judicious in how often and how many soil parameters you tweak. Otherwise, you will just lose control of your understanding of how the ground is controlling your structure-ground interaction performance. So we, we started with the A-star parameters based on Easington and O'Brien, and then as we got data, we back-analysed in our model and derived what we thought were better A-star parameters, which were called in the slideshow the modified A-star. And then we fed those back into the model, but obviously we didn't have time to do umpteen iterations, so we had a few iterations at that. And then what you're doing is looking at the match between your measured deformation and the deformation you're getting out of the model. And you just have to say, okay, we're close enough for all engineering purposes.
Thanks.
Michael Van Sass from MacDonald. David, the 14-week saving sounds like a really a big number that contractors certainly would want to get on board in the future. Do you see this sort of process now filtering down into other projects, or do you think it is such a site-specific case that other large-scale infrastructure projects are unlikely to take this approach on?
I think the industry as a whole has moved on. I think what you need to appreciate is that the Crossrail engineering design standards, by the time we started the design, let alone by the time we finished the design, were based on the way things were done a decade or more ago. We have progressive, through the Syria documents, improvement, I think is the right word, of how to invoke the observational method in these big engineering projects. So I would like to think that with this case history and other examples from projects in the last decade, say, that there is enough knowledge within the industry to take this sort of approach and to actually find ways of delivering projects more cost effectively. And cost effectively, this project, it wasn't so much less material, it was less construction time. Because, you know, that 14-week delay, that was going to delay a lot of other contracts, most critically the TBM. And, you know, the TBM could not recover any of that. And then you're into track laying. So, you know, everything cascades down on the critical path.
Thanks.
Okay, it's Chin Kang Shen from MacDonald. Yeah, actually, I was in the C121 side, spread concrete lining side, so so I definitely know what's happening if the program delay and all these TBN and also the tunnel station tunnel enlargement works will be delayed. And I have a question for you, Dave. You mentioned about the iteration of the soils. I was wondering, the wall itself, the stiffness, especially the stiffness of the wall, after we consider, for example, the rim beams, do we did this iteration of the wall property as well? I mean, the concrete wall properties.
The actual stiffness of if you take a unit length of the diaphragm wall, which is 1200, I mean, that was unchanged. Obviously, as the excavation went down and the ring beams were built, then the stiffness of the ring beams was added into the model. So the shaft structure became stiffer. And conversely, the so-called strutting wall was removed from the model with the excavation.
So it means it's a separated elements to consider. I mean, one element is the rim beam, the other element is the wall. What do you
yes.
Thank you.
Yeah, I mean, you know, there's a lot of elements. I mean, I forget what it was. It was 120,000 shell elements, which represented the structure. By the time we had the whole structure built, that was the shaft with its internal ring beams, plus all the surrounding tunnels.
David, I thought that was a very good presentation, and it's a very good project, and I think you presented it very well. And taking on board your points about the experience in London clay, I think being involved in Dean Street box, and we've had similar learning experience in terms of undrained versus drained for London clay experience, and this does make a lot of difference to the model. We also got involved in trying to transfer some of the experience in Dean Street into the Moorgate box, and it did duplicate the same learning experience. So that means you can move stuff from part to part of the London clay, which is important, I think, in the future. Taking on board the lessons learned, I think the new Syria Guide 780 now enables you to look at the observation method. It puts forward 4 approaches, but one based on ab initio, which is the way you've dealt with it initially, which is on a clear view on design parameters, starting conservatively, but then taking up the options improvement, which is a safe way to start. It also deals with the option of an unforeseen event coming on, which is ipso tempore, and how does one control an excavation which is something's changed during the course of the works. And I think the proper experience that you've got there is important when you do see something going wrong. And it's interesting to compare that with other parts of the world. In Singapore, they do loads of excavations with cross-wall props, and they get it, and it's not a problem. And you say this is an issue they should take care of, and they're not that interested. But I think there is an issue with the type of clay that you deal with cross props. I think if you're in soft clays, you can clean the wall off nice and easily, and the tools do the job. I think in London clay, if you've got some overbreak and you try and go below it, then it won't get that material off, and the clay is just a bit too stiff, and the cleaning methods just aren't up to it. So there is a difference in different parts of the world in my experience. And I wondered whether you'd make another comment on the issue of grouting up the wall, and whether you think the grouting operation actually forced the wall over or not. Or I never really looked at the data that much to see whether it's pushing the wall over or whether it's this progressive movements, but I'd be interested in comments around that.
Yeah, thank you for that. Yeah, I agree with you. The latest Syria guide has exactly got those wonderful Latin terms. Why we use Latin in this day and age, I'm not quite sure. But very much we were changing things as time went by, which is what the second of the terms you use means, really. And I think that is an approach. I think in order to adopt that approach, you need engineers doing the design who are well versed, and you need a client who actually understands what it's all about. And I have to say, Crossrail in that regard were an excellent client, a doubly excellent client, because they also positively encouraged people working on the project to write papers describing what had been done, which obviously are going into the industry as case histories, which also is very good. I have to say, I have seen a couple of excavations collapse in Singapore in my time, but I think I would agree with you. My recollection of clay in Singapore is it's a bit more like toothpaste, whereas what we've got in that blue London clay is more like soft bricks. Your comment on cleaning the wall, a sort of wire brush, clearly wasn't man enough to do the job. And I think, hindsight's a wonderful thing. And the engineer ideally would have dug his heels and said no, but then we didn't have the case history to tell you how it went wrong. Now we do, so hopefully it wouldn't even get proposed in a London clay scenario. Sorry, what was your last point again? Oh, the grouting, yeah. That's an interesting one. We had an amount of data. Obviously, we had the movement of the wall, and we did have the dates when grouting was injected, and it was over, I think, at least 3 separate phases. I think I wouldn't say the jury's out. I think we were ourselves convinced that it was a contributory factor in the ratcheting effect in terms of the lesser recovery specific to the east wall when compared with the other 3 walls. But I haven't seen any work done specifically to drill down into that to at the next level to try and correlate volumes of grout and all that sort of thing. And I guess that won't happen now. But certainly, I think the evidence was more than just circumstantial.
Ron Williams from formerly Mott MacDonald. Somebody in my generation, this is just absolutely amazing. It's absolutely amazing when I think of the environment, of the antipathy between contractors and consultants. A client that was not often up to speed, and to see the whole thing come through is absolutely amazing, actually. And in terms of transfer, the experience of having a good client is the absolute critical thing. And clients don't always stay good. They go through periods of change themselves, commercial and other changes. And this issue about the ability to transfer from one project to another is highly dependent on this issue of the quality of the contract of the client. And the other point you made about the UK and international experience, my experience has been that you don't often get a client as good as Crossrail, and it's much more difficult, and therefore you need to be more conservative in those circumstances. But this is one of the most brilliant examples of this form of construction that I've ever seen. It's fantastic.
Yeah, thank you, Ron. I mean, I will just say once more, I think Crossrail were a very good client in the respect of they were able to listen to their design engineers and understand what we were saying and have the confidence in themselves to believe that we could deliver what we said we were going to. So all credit to them for that. Certainly I've worked with other clients in the UK where they have not within their own ranks had people with the technical knowledge to take that approach. And obviously there are reasons why clients set themselves up with a very low technical skill base, shall I say. You know, that's the way of the world. But as designers, which I imagine quite a lot of us in this room are tonight, you know, part of our skills is not only just to do this sort of what I might call high-end analysis, but also to persuade clients that they should take us on to do it for them because they will benefit.
Any more questions? Okay. Thank you again, David. That's great.
Thank you.
Yeah, and thank you all for attending and for participating in the Q&A at the end. Just got a few points to mention before we go for some sponsored drinks in the lower library. We have some upcoming events. So we've got a summer break, which you'll be gutted about, I'm sure. And then on the 6th of September, an evening meeting, Tunnelling Ground Risk, a perspective by Dr. Chris Menkiti. And then on the 11th of October, we have another evening meeting, A Brief History of Construction Monitoring in England, Peter Shewitt from Lang O'Rourke. And then we also have that month a conference, Ground-Related Risk to Transport Infrastructure. So the call for abstracts is now closed, but registration is now open via the website. So please get involved in that. It should be a really good conference. And then in November, we obviously have the Glossop again this year. And as you all know, Jackie Skipper will be presenting on variability in ground hazards. How does the ground get to be unexpected? We've also recently just awarded the Glossop Award to Gemma Sherwood of Atkins, who presented a really fantastic presentation on her experience on site supervision for the construction of Hinkley Point C nuclear power station. So it would be well worth turning up early for that meeting. And then to finish off the year, as we always do in December, new UK geotextile standards from Steve Corbett and Ian Fraser. That's our joint meeting with the IGS. So thanks again for coming, and if you'd like to join us now in the lower library for some sponsored drinks, that'd be great. Thank you again.